Hello, everyone. While we live an ordinary moment, breathing, blinking, thinking about tomorrow, something enormous is happening that we cannot feel. Something is pulling the universe apart, gently, relentlessly, without noise. Between every galaxy, between every star, and between the atoms that make up your body, there is space. And that space is stretching. Not like a rubber band you can watch with your eyes, but like a law written into reality itself. The cosmic ocean is widening, and the islands of matter are drifting away from one another. We float on a vast sea where distance grows by itself. And the strange part is this: the more empty a region is, the more easily it seems to expand. The emptiest places become even emptier. The quiet gaps swell. The separations become permanent. Scientists call the driver of this accelerated expansion dark energy, a name that sounds like an answer, but is mostly a label taped onto mystery. According to the best measurements we have, dark energy makes up roughly about 70% of the total energy content of the cosmos. We do not see it directly. We do not catch it in a jar. We infer it from what it does. It pushes, it accelerates, it widens the void. And if you like calm journeys to the edges of what we can know, then settle in. Let your shoulders drop. Let your jaw unclench. Tonight we drift slowly, like a spacecraft with its engines off, letting the universe reveal its shape. Because the first surprise is not dark energy. The first surprise is how empty everything is. Look around you at the room you're in, the walls, the air, the familiar weight of objects. It makes the universe feel solid and rich. The ground beneath your feet suggests that reality is mostly stuff. But when astronomers add up everything, we can see the stars, the glowing gas, the galaxies, the planets, and all the atoms that might someday become life. What we call normal matter is only a small fraction of the whole. Even within that small fraction, matter is spread incredibly thin. On average, across the cosmos, the density is so low that in a volume as large as a cubic meter of deep space, you might find only a handful of atoms, mostly hydrogen, wandering like lonely grains of sand in a cathedral. If your room were emptied, truly emptied, you would still be standing in air that contains billions of times more particles than the same volume between galaxies. Deep space is not kinda empty. It is emptiness refined. Yet this emptiness is not random. It has architecture. With satellites like Planck and long years of patient observation from telescopes like Hubble and its successors, we have mapped the distribution of galaxies across immense distances. What appears is not a uniform fog of stars, but a structure, an enormous cosmic web. Matter gathers along filaments and walls. Galaxies cluster at intersections, like dew collecting where threads cross. Between these glowing strands lie vast regions with far fewer galaxies, enormous, dark, quiet volumes that astronomers simply call voids. The word is plain. The reality is not. Imagine the universe as a boundless ocean at night. Galaxies are not evenly dissolved like salt in water. They are more like foam on the surface. Thin, bright, delicate patterns. Beneath and between that foam, there are giant bubbles of darkness where almost nothing lives. We live on one of the bright threads, And the darkness is not just around us. The darkness is growing. You might wonder why that matters, why the voids should be important if they contain so little. The answer is that voids are not mere leftovers. They are active participants in cosmic history. They are places where expansion shows its purest face, where gravity has less grip, and the stretching of space becomes more obvious. For a long time, many scientists expected the expansion of the universe to slow down. After all, gravity pulls, it gathers. It should act like a brake on cosmic motion. But in the late 1990s, two independent teams studied distant supernovae, exploding stars, used as cosmic mile markers, and found something that felt, at first, like a mistake. The expansion was not slowing. It was speeding up. The universe was not just opening. It was opening faster and faster, as if an invisible hand were turning the dial. That discovery reshaped cosmology. It also carried a strangely emotional weight. The idea that the universe is not simply drifting, but being pushed apart by something we do not yet understand. And from that moment, the voids became even more haunting. Because in the emptiest places, the push appears to win more cleanly. Gravity can hold galaxies together inside clusters and bind stars within galaxies and hold planets in their orbits. But across huge intergalactic gaps, the expansion becomes dominant. The cosmic web stretches, the strands thin, the separations widen. We live in a lucky era, a brief era, when galaxies are still visible to one another across great distances. It will not last forever. Forever is a word the universe challenges. If the accelerated expansion continues, the night sky of the far future will grow poorer. One by one, distant galaxies will slip beyond a boundary where their light can never reach us again. This boundary has a name too: the cosmic event horizon. It is not a wall you can touch. It is a consequence of expansion. If space between us and a distant galaxy stretches fast enough, then even light traveling at its ultimate speed cannot cross the increasing distance. The light moves forward locally, but the distance grows faster than the light can close it, like trying to swim upstream in a river that accelerates without limit. Beyond that horizon, galaxies still exist. Stars still burn. Maybe life still rises and wonders. But their signals can never reach us, and ours can never reach them. For us, they become causally disconnected, gone from our practical reality. It is a cosmic form of separation, not destruction of matter, but destruction of connection. And this, in a quiet way, is one of the most tragic ideas in modern science. Dark energy does not necessarily smash galaxies. It makes them unreachable. It erases the possibility of reunion. Now, to understand how strange that is, let's slow down and hold the picture in your mind. Picture two galaxies, 100 million light years apart, already a distance so large it turns imagination into fog. The galaxies are not moving through space like ships across water. Instead, space itself is stretching between them. The coordinates of the universe change. The cosmic map expands. In everyday life, we think of distance as a stable thing. On cosmic scales, distance is dynamic. We do not feel this expansion because local gravity and local forces are strong. Atoms, stay atoms. The Earth stays Earth. The solar system stays bound. The Milky Way remains a galaxy. Inside those structures, the expansion is overwhelmed. But in the deep, thin, weakly bound regions between clusters of galaxies, expansion rules. And here, the story becomes bigger. Because the large-scale shape of the universe is a tug-of-war between two invisible characters. Gravity, which gathers matter and builds structure. Dark energy, which drives the expansion and pulls structure apart on the largest scales. This tug-of-war creates the cosmic web. Gravity pulls matter into filaments. Voids are left behind. Then, dark energy makes those voids swell even more. Simulations run on powerful supercomputers begin with the early universe slight fluctuations in density after the Big Bang and let gravity do its work for billions of years. Over and over, the same pattern emerges. Matter collapses into threads and nodes, and the spaces between inflate into enormous, empty volumes. It is not science fiction. It is a structure we can measure, and yet there are hints that reality is even stranger. Some observations suggest that voids can expand a bit faster than simple models predict. Not wildly faster, but enough to make scientists watch carefully and argue carefully and measure again. The universe rarely shouts. It whispers discrepancies. Now, let's step deeper into one of these voids. Not physically, no spacecraft today could cross such distances quickly, but with the mind's quiet camera. A typical cosmic void can be hundreds of millions of light years across. In a region like that, you might travel for an unfathomable stretch and find only a few galaxies, thin, scattered, dim. Compared to our own neighborhood, where dozens of galaxies share gravitational ties, a void is a near refusal of structure. One famous example is sometimes called the quietest void, a huge region discovered in the late 20th century, startling for how few galaxies it contains compared to what should be there. A place where, by ordinary expectations, thousands of galaxies might reside, but only a small number are found. A space so empty that if our own galaxy sat near its center, the night sky would feel profoundly different. There would be no bright neighboring galaxies displayed like lanterns in the cosmic distance. There would be far less to see. The universe would look small, not because it is small, but because visibility has been stolen. This is one way the cosmos shapes perception, by deciding what can be seen. And once you appreciate that, another unsettling thought arrives. Maybe emptiness is not merely absence. Maybe emptiness is a kind of active medium, an arena where the fate of everything is decided. When we say dark energy fills space, we do not mean it's like gas in a room. It does not clump. It does not form clouds. But it behaves as if empty space carries an energy of its own, so that as the universe expands and creates more space, there is more of this energy in total. That is a chilling idea. Expansion creates the conditions for more expansion. It is why accelerated expansion feels like a feedback loop written into the fabric. In the early universe, When matter was dense and everything was close, gravity dominated. Dark energy was there, but it mattered less. As the universe grew and matter diluted, dark energy became relatively more important. Eventually, it took the lead. We live after that turning point. Now, let's pause the cosmic motion for a moment and look at another invisible scaffold holding the universe together, another thing we cannot see directly but cannot deny: dark matter. Because while dark energy pushes the largest scales apart, dark matter acts like hidden mass, providing extra gravity that helps build the cosmic web in the first place. The story of dark matter begins with a simple confusion. In the 1930s, astronomers studying galaxy clusters noticed that the visible matter did not seem to be enough to keep those clusters bound. Galaxies were moving too fast. By ordinary gravity, the clusters should have flown apart long ago, but they didn't. Later, in the 1970s, careful measurements of how spiral galaxies rotate showed an even clearer puzzle. Stars far from the galactic center were orbiting too quickly. If only visible matter existed, their speeds should drop with distance. They did not. They stayed high, as if each galaxy were embedded in a vast halo of unseen mass. That unseen mass is what we call dark matter. It does not emit light. It does not absorb light in the usual way. It does not shine. And yet, it bends light through gravity, acting like a lens. It shapes the motion of galaxies. It helps pull ordinary matter into the filaments of the cosmic web. Simulations of structure formation fail without it. With it, they match the universe we see. So now we arrive at an astonishing inventory. Roughly about 5% of the universe is the familiar matter that makes stars, planets, and bodies. Roughly about a quarter behaves like dark matter, exerting gravity without light. Roughly about 70% behaves like dark energy, driving accelerated expansion. In other words, most of reality is invisible to our senses. We live inside a cosmos that is mostly made of things we cannot directly touch, see, or bottle. This is not meant to make you feel small in a cruel way. It is meant to make you feel honest awe, because it means the everyday world, the warm lamplight, the texture of a blanket, the softness of breath, is built atop a much larger stage than our instincts ever evolved to imagine. Now, if the story ended here, it would already be enough. Dark energy pulling the universe apart, dark matter holding it together, visible matter floating as a thin froth between them. But the cosmos has a habit of offering one more layer of unease just when the mind thinks it has reached the bottom. So now we approach something even quieter than dark energy. Not the slow erasing of connection, but the possibility of an abrupt rewrite of the rules. This idea comes from quantum physics and the nature of what we call vacuum. In everyday language, vacuum means emptiness. But in modern physics, empty space is not truly empty. It contains fields. It contains energy fluctuations. It is, in a subtle way, alive with possibility. And some theories suggest that the vacuum state of our universe might not be the absolute lowest energy state possible. It might be metastable, like a ball resting in a shallow dip on a hillside, rather than safely at the bottom of the valley. If that is true, then the universe could, in principle, fall into a lower energy state through a quantum event. This hypothetical process is often described as false vacuum decay. Imagine a bubble forming somewhere in space, tiny at first, like a microscopic flaw in glass. But this bubble would not contain ordinary space with ordinary physics. Inside it, the constants and rules could be different. The very structure that makes atoms stable might change. And the boundary of that bubble would expand outward at nearly the speed of light. If such a bubble ever formed within our cosmic neighborhood, there would be no warning. No signal could outrun the bubble's edge to tell us it was coming. One moment, the sky would look normal. The next moment, the local rules of matter could simply stop matching what we are. It is one of the most terrifying ideas, precisely because it is so silent. Now, to be clear, this is speculative. It is a theoretical possibility suggested by certain measurements and models, not a confirmed impending event. The universe may be stable for times far longer than any human story. But the fact that physics even allows us to ask the question that stability might be a delicate thing is itself unsettling. The cosmos may not only drift toward loneliness, it may also, in principle, contain traps in the mathematics. And if that feels heavy, remember, you are not required to carry this fear. We are exploring ideas, like walking past a dark ocean at night, noticing its size, then returning to the warm shelter of the shore. Because the purpose of calm science is not to frighten you awake. It is to make the mind quiet with perspective. Now we turn to another kind of cosmic silence, one that feels personal to the human imagination, the silence of other minds. We look at the sky and we see billions of stars in our galaxy alone. Modern surveys suggest that planets are common. Many stars may have rocky worlds in temperate zones where liquid water could exist. So a simple, naive thought follows. If life is not extremely rare, then the cosmos should be loud with civilization. We might expect signs, engineered structures, powerful radio beacons, deliberate messages, unmistakable patterns that nature is unlikely to create. And yet, when we listen, the sky is quiet. This is often called the Fermi paradox, named after a physicist who supposedly asked, in a casual moment, a question with a sharp edge. Where is everybody? We can build equations that suggest many civilizations could exist. We can model the spread of self-replicating probes across a galaxy on timescales far shorter than the age of the Milky Way. And still, our instruments find no clear evidence of company, only cosmic background noise, pulsars, and the natural radio whispers of stars and plasma. The silence might mean we are rare. Or it might mean civilizations do not last. Or it might mean they choose to hide. Or it might mean our listening methods are naive. Or it might mean the universe has filter stages so difficult that most life never passes them. One idea is called the Great Filter, a bottleneck somewhere between lifeless chemistry and a galaxy-spanning civilization. Perhaps the filter is behind us. Maybe the origin of life is unbelievably improbable, and we are a statistical miracle. Or perhaps the filter is ahead. Maybe technological species tend to destroy themselves, or be destroyed by cosmic events, or simply fail to survive long enough to be visible. The unsettling part is not any single explanation. The unsettling part is that we do not know which one is true. And while we wonder, the cosmic event horizon is still doing its quiet work. As expansion accelerates, the number of galaxies we can ever communicate with shrinks. Even if someone out there shouts with all their power, the stretching space can make their message impossible for us to receive, not because we lack technology, but because causality itself sets the limit. This adds a strange urgency to the search for life. If contact is possible at all, the window may be limited not by our patience, but by the geometry of space-time. In the far future, if dark energy continues as it appears to, our local group of galaxies, Milky Way, Andromeda, and a handful of smaller companions will remain gravitationally bound, while more distant galaxies slip away beyond the horizon. For astronomers living tens of billions of years from now, the night sky may contain only their own merged galaxy and nothing else. And that future civilization, brilliant as it may be, could find itself trapped inside a misleading cosmic bubble. With no distant galaxies to measure and no detectable relic radiation of the Big Bang, they might conclude quite reasonably that the universe is static and small, not because they are foolish, because evidence can be erased. This is what makes accelerated expansion feel like an eraser, not just of connection, but of history. We, in this era, are able to see far enough to piece together a cosmic story. We see many galaxies. We detect the faint afterglow of the early universe. We measure expansion. We infer dark components. We are perhaps living in a temporary golden age of cosmological information, and that has a bittersweet flavor. We may be among the last beings in our region of the cosmos who can ever reconstruct the true scale of what exists. Now, take a slow breath, because the story is about to widen again. If you're still with me, drifting gently through the ideas, then we can let the universe keep expanding in our imagination without rushing, without gripping too tightly. Because the far future is not something we will live through. It's something we can observe with the mind, the way we observe waves from the safety of the shore. And the far future begins with a simple truth. Stars do not last forever. They feel eternal only because human life is brief. A star is a furnace, fueled by gravity and nuclear reactions. It shines because it burns through a supply of hydrogen and other elements, transforming mass into energy and light. Every sunrise you have ever seen is the visible trace of a process that consumes a finite budget. The universe is generous with time, but not infinite with fuel. Over billions of years, galaxies convert cold gas into stars. Stars fuse light elements into heavier ones. Massive stars burn fast and die young, sometimes in spectacular supernovae. Smaller stars burn slowly and endure. But even the most patient stars have an ending, and as the universe expands, something else happens alongside the slow burning of fuel. Matter becomes more spread out. Gas clouds find it harder to collapse and ignite new stars. Galaxy collisions, one of the great triggers for star formation, become rarer. as galaxies drift apart and become unreachable. So the sky's brightness has an arc. It rises, peaks, and declines. In many models, the peak era of star formation is already behind us. The universe, in a sense, has already used much of its easiest, richest supply of star-making material. The cosmic fireworks are not over yet, but they are no longer at their loudest. In the far future, trillions of years from now, new star birth may become rare, then stop altogether. Not because the universe becomes dramatic, but because it becomes diluted. Spread too thin, quietly, the universe begins to live off its savings. The last patient stars. When bright, hot stars fade, the universe is not immediately dark. It becomes dominated by small, cool stars, red dwarfs. These stars are miserly with fuel. They can sip hydrogen for extraordinarily long times. In that era, the night sky, if anyone exists to look up, may be lit by dim, steady embers rather than brilliant suns. It would be a calmer cosmos, colder, redder, slower. Eventually, even those embers go out. And when the last red dwarfs finish their long lives, there may be no new stars to replace them. Then the universe begins to enter a new phase, not a sudden ending, but a gradual settling. The era of starlight gives way to the era of remnants. The universe of remnants. After stars die, they leave behind bodies that are less like fires and more like stones. White dwarfs, the hot cores of sun-like stars, slowly cooling for unimaginably long times. Neutron stars, dense and exotic, sometimes spinning and pulsing, eventually slowing. Black holes, the deepest wells of gravity, gathering matter and light and keeping secrets behind horizons. These objects linger. For a while, they define what structure remains. But the universe is patient, even with remnants. And time, on cosmic scales, is a solvent. So now we come to one of the most inevitable and least cinematic ideas in physics. Heat death. Heat death, the universe's quiet exhaustion. Heat death sounds like an event, but it's more like a condition. It comes from the second law of thermodynamics. In a closed system, entropy tends to increase. Energy spreads out. Differences even out. Temperature gradients fade. The ability to do useful work declines. On Earth, you see this when a hot drink cools to room temperature. The energy is still there, but it is more spread out, less organized, less able to drive change. Now scale that idea to the entire universe. As time passes, energy distributes itself more evenly. Stars radiate their heat into space. Remnants cool. Even black holes, in a very slow and subtle way, do not remain perfectly stable. When temperature differences disappear, there are no engines left, no flows that can power complex activity, no chemical cycles, no weather, no metabolism, no computation as we commonly understand it. In the heat-death picture, the universe doesn't explode. It simply becomes unable to do much. It becomes a place where change is increasingly rare, where everything settles into a thin, cold, uniform hush. If dark energy continues to drive accelerated expansion, this hush becomes even more final, because expansion helps separate everything, reducing the chances of interaction. A lonely particle can't collide with neighbors if there are no neighbors within reach. And then, even the loudest objects left the black holes begin their slow exit. The slow evaporation of black holes. Hawking radiation. For a long time, black holes were imagined as eternal. Once formed, they would last forever, swallowing and keeping. But quantum physics complicates that picture. In the 1970s, Stephen Hawking showed that black holes are not perfectly black due to quantum effects near the event horizon. They should emit a faint radiation, now called Hawking radiation, and therefore lose mass extremely slowly. To human instincts, this is almost impossible to feel as real because the timescales are so absurd. A stellar mass black hole takes an unimaginable duration to evaporate. A supermassive black hole, the kind sitting in the center of galaxies, takes longer still, in times that make the current age of the universe look like a brief spark. But almost forever is not forever. If time continues, the black holes shrink. As they shrink, their temperature rises, and near the end of their lives, they release their final energy in a last burst. In a universe where almost everything else has already fallen silent, these final black hole endings would be among the last fireworks. And then, when the last black holes evaporate, something profound happens. The cosmic stage loses its heaviest actors. The large gravity-bound structures that once held matter together are gone. What remains is mostly radiation and sparse particles, spread so thin that interactions become nearly non-existent. At that point, the universe approaches a condition that feels like true stillness, cold, dark, and vast beyond meaning. Even matter may not last. The question of proton decay. There is another possibility, even quieter than black holes fading. Some theoretical frameworks suggest that protons, the building blocks of atomic nuclei, may not be absolutely stable. They may decay, but so rarely that we would need immense amounts of time to see it happen. Experiments have searched for proton decay in deep underground detectors, shielded from cosmic rays, watching huge volumes of matter for the faintest sign of a proton's disappearance. So far, there is no confirmed detection. That could mean protons are stable, or it could mean the decay time is simply far longer than our experiments can currently sample. If protons do decay, then over unimaginable timescales, even the last cold objects, white dwarfs cooled into dark remnants, planets frozen into silent lumps, would gradually dissolve. Matter would not remain as matter. It would become lighter particles and radiation. It would be a universe where even the idea of a thing becomes difficult to sustain, not because something attacked it, because time, given enough room, unthreads it. A different ending, big rip if dark energy changes. So far, we've assumed dark energy stays roughly constant in time in the simplest fit to many observations. But there is a more dramatic theoretical possibility, often called the Big Rip. This is not the default expectation. It is a scenario that becomes possible if dark energy grows stronger over time. If that happened, the accelerated expansion would not only separate galaxies, it could, in principle, overpower gravity at smaller and smaller scales, eventually tearing apart galaxy clusters, then galaxies, then solar systems, then planets, and, in the extreme version, even atoms. It is a frightening idea because it takes the gentle eraser and turns it into a shredder. But it is also important to hold it responsibly. This is a speculative branch, dependent on what dark energy truly is. Current evidence does not require a big rip. Many models favor a calmer long-term separation rather than a violent local tearing. Still, the big rip has value as a thought experiment because it highlights the central truth. We do not yet fully understand the agent shaping the universe's future. We can measure its effects. We can map its consequences. But we do not yet hold its nature. And in science, that humility matters. The deepest loneliness, when the sky forgets. Now let's return to a quieter tragedy, one that doesn't require a big rip, only the steady continuation of accelerated expansion. As galaxies pass beyond the cosmic event horizon, the observable universe becomes smaller in practice. Fewer objects remain visible. The sky grows emptier. Eventually, for a civilization bound to a gravitationally tied group of galaxies, the wider universe could become invisible. Not because it vanished, because it became unreachable. And then something odd happens. The cosmos becomes harder to know. A future astronomer might look out from their world and see only their local galaxy. No distant galaxies to measure redshift. No easy evidence that space is expanding. No detectable afterglow of the early universe. The clean clues we use today, our cosmic fossils, would have faded beyond detection. That future science would not be stupid. It would be starved. And this is a lesson that feels almost philosophical. Knowledge depends on what remains observable. The universe is not obligated to preserve evidence for us. It does not curate its own museum. It just unfolds quietly. The great silence and the great filter revisited. And here, the silence about other civilizations becomes even heavier. Even if the universe contains many intelligent species, accelerated expansion narrows the window in which they can discover one another. It imposes communication limits that no technology can outsmart, because the limit is not engineering, it is geometry. The great filter idea returns with extra sharpness. Maybe advanced civilizations are rare. Maybe they burn out quickly. Maybe they never become loud. Maybe the cosmos is full of brief sparks that never overlap in time. Maybe the universe's expansion makes overlap hard, even when sparks exist. If you imagine a galaxy as a vast, dark forest, civilizations are like campfires. Some light briefly, some burn longer. But if the forest itself is being stretched, if the trees are being pulled apart so that sound and light can't carry as far, then even many campfires can feel like solitude. And solitude shapes the story a species tells itself. Now, as we move deeper into the far future, the story gets stranger, because when events become rare, physics invites unsettling questions about what can happen given almost infinite time. That's where we encounter one of the most eerie thought experiments in cosmology. Boltzmann brains, a strange mirror in infinite time. In a universe approaching heat-death, cold, thin, nearly uniform quantum mechanics still allows fluctuations, extremely rare, extremely small, but not forbidden. If time goes on long enough and space is large enough, then even very unlikely arrangements can occur by chance. A clump of particles forming briefly, a structure assembling, a pattern emerging from noise. Then, in that extreme limit, some physicists consider whether a random fluctuation could assemble something as complex as a self-aware mind, complete with a moment of consciousness and a set of false memories. This hypothetical entity is called a Boltzmann brain, not because anyone expects to find one tomorrow, but because its possibility creates a conceptual tension. If the future lasts essentially forever and fluctuations continue, then random, brief minds might outnumber ordinary evolved minds like us. It's a disturbing idea because it points at a deeper question. What does it mean for an observer to be typical? And it also pokes at the nature of evidence, memory, and reality, because a random mind could remember a life that never happened. If you let this idea get too close, it can feel like existential vertigo. So we hold it gently, the way you might hold a strange shell you found on a beach. You don't need to build your home inside it. You just notice it exists, and then you set it down. Because the point tonight is not to trap you in cosmic dread. It's to widen your perspective until the mind stops clenching. Boltzmann brains are interesting because they show how far physics can stretch imagination when time becomes vast. But your experience, your breath, your warmth, your bed is here, now, and real, in the only way that matters for living. It is the reality you inhabit. So we step away from the edge, and we bring the scale back down. A quiet synthesis, what the universe seems to be doing. If we gather the threads of what we've drifted through, we get a calm but astonishing picture. The universe is mostly empty, and the emptiness is structured into vast voids. Matter forms a cosmic web, guided by gravity and shaped by dark matter. Expansion is accelerating, likely driven by dark energy, making distant regions increasingly unreachable. The far future tends toward darkness and dilution, fewer stars, less structure, fewer interactions. Over extreme times, even black holes may fade, and perhaps even matter itself may dissolve into radiation. In the deepest future, change becomes rare, and the universe approaches a kind of cosmic stillness. It is not a story of a villain. It is a story of laws playing out. And inside that story, something tender appears. We are living during a relatively bright window. A window where the universe is still busy enough to be interesting, still warm enough for chemistry, still structured enough for planets, still young enough for starlight. Not forever, but long enough for you to exist. Long enough for minds to look up. Long enough for a species on a small planet to invent telescopes and ask what darkness means. That, in itself, is remarkable. The return from cosmic scale to quiet sleep. Now we let the cosmos keep expanding without us. We don't chase it. We don't try to solve it in one night. We allow the universe to be vast and allow ourselves to be small in a comforting way, not insignificant, just unburdened. Because your body does not need to hold the universe. Your body only needs to rest. So bring your attention gently back to the room you're in. Notice how gravity holds you, firm, patient, constant. The same force that gathers dust into worlds and worlds into systems is also the reason you can relax into your bed. You are supported. You don't need to do anything to be held. Let your breathing slow. In and out. The universe expands. Quietly. Your breath moves. Quietly. And both can be true at the same time. If thoughts arise about dark energy, about distant horizons, about the far future, let them float past like dim satellites crossing a night sky. No need to follow them, no need to catch them. Just watch them fade. Your eyelids can be heavy now. Your face can soften. Your tongue can rest. Your shoulders can sink as if someone gently removed a backpack you forgot you were wearing. Let the muscles in your legs unclench. Let your hands rest open. Let your chest rise and fall without effort. On cosmic scales, the universe is learning how to become still. On human scales, sleep is how you become still, a small daily echo of a larger rhythm. And if it comforts you, you can imagine the darkness not as an enemy, but as a soft blanket, an environment where nothing is demanded of you. Darkness as permission, quiet as safety. The sky outside may contain billions of stars, and beyond them, the vast architecture of emptiness. But here, in this moment, your world is reduced to the simplest things: breath, warmth, weight, rest. Everything else can drift beyond your own little event horizon for the night, beyond reach, beyond concern. And you can let the mind dim the way distant galaxies dim, not because they are gone, but because it is time to stop looking, time to stop measuring, time to stop carrying. Just as the universe keeps its secrets without hurry, you can keep your worries without urgency, because you don't need to solve them right now. You can sleep. And in sleep, the mind becomes a quiet space again, wide, dark, and gentle. A calm void, not empty in a frightening way, empty in a restful way, a place where the noise of the day cannot survive. Sweet dreams.